Hi everyone, so this is going to be topic D.7. Before you move on to this topic, make sure that you've gone through topic 20.3, which is on isomerism, and go specifically through optical isomerism if you have to really get into this one. So in this topic, we're going to be looking at a drug which is called Taxol, and this drug was initially synthesized from natural substances, but the problem arises when the demand for this drug is greater than what naturally you can provide. Hence, we had to use lab synthesis to meet the high demand of this drug. So if you remember when we did optical isomerism in topic 20.3, we said that even if we have two enantiomers that have the same chemical reaction, our body can react differently to different enantiomers. When I mention enantiomer, so this is one enantiomer, this is a second enantiomer. These two are optical isomers. And for example, if you look at limonene plus limonene and minus limonene, your body smells them and tastes them differently. So one tastes like lemon and the other one tastes like peppermint, but they look exactly the same except that they are mirror images to each other. So when optical isomers go into receptors of the body, because we're dealing with enzymatic reactions and that you have the lock and key mechanism that specifically the molecule has to fit in the enzyme in a particular way. So if this is the enzyme, the molecule has to fit in a very specific way. So that mirror images do not fit, right? So, for example, here I have the chiral center, right? So, this is the drug binding site. So, this would be like the enzyme, let's say. So, here it fits. You can see here. Here you have the mirror image of that enantiomer. So, this is the active enantiomer. So, you can see that the active sites fit, but in the inactive enantiomer it does not fit, but the molecule is exactly the same except that it's mirror images. They are mirror images of each other. So when we're synthesizing the molecule, we have to be very careful on what enantiomer we are producing. Now we're going to look at the case study of Taxol. Taxol is the trade name, and the drug is known as paclitaxel. Trade name is Taxol. It's a really complex molecule and it has 11 chiral centers. Pause the video, try to look for these chiral centers, and then you can play it again to see if you've got those 11 chiral centers. Taxol is used to treat several forms of cancer. It's a chemotherapeutic drug, which means that it's effective against many types of cancer. And it works by interfering with tumor cell division. So it binds to certain proteins called tubulins and prevents more tumor cell to be formed. If you go on page 4, you are going to see a little bit more detail on how Taxol acts as an anti-cancer. So what happens is that Taxol will bind to tubulin in cells. Those who do biology will understand this a little bit better. So this is a cell dividing. So we have one cell, this is the parent cell, and this is normally what you would get. Two daughter cells. So you have the cell membrane and then the nucleus here, right? So when a cell is dividing normally, so what happens? So this is the genetic material, what we know as the chromosomes. So the genetic material is going to separate into two. equally. And these things are called spindles, right? So the chromosomes are attaching to the spindles and then are dragged to two different parts of the cell, and then it's going to divide into two daughter cells, right? Now what happens, the taxol is going to bind to the spindles, and when the taxol binds to the spindles means that the genetic material cannot be properly distributed into two cells. And when the genetic material cannot be distributed, you end up with having like a cell in a big mess. So then the cell dies, right? So this is how taxol work. It says here, the tubulin is the main component of microtubules which form structures called spindles. So these are the spindles here. These are the spindles, and the spindles here, they contain a substance called tubulin, right? And the taxol will bind to the tubulin. When the taxol binds at the microtubules, it prevents the spindle fibers from breaking down, and this halts the cell division cycle, right? So it prevents the growth of the tumor. So the genetic material cannot divide into two, and then the cell dies. It was first extracted from bark of yew tree, so it was initially obtained naturally. Now, when we used to make taxol from those trees, it was a very wasteful process because a lot of it was used and the process was not efficient. And the problem is that those trees were threatened. So then from this, a semi-synthetic method was developed. So we used part of it which was natural, and then from the natural precursor, we produce taxol. So it is a semi-synthetic method from the leaves of different but more common and fast-growing yew trees. And the natural precursor is called DAB. DAB is for short of this. This is the DAB molecule, and this is an overview of all the steps. Now, when we carry out all the steps, this is a very low yield process, and the yield to make taxol from the yew tree bark, that was 0.004%. But when we do the semi-synthetic method, this method addresses the different environmental concerns, which means that those leaves, which take about 200 years to mature, so we have stopped using these, and we're now using the European yew leaves. And now, from that precursor, which is from these leaves, the yield is 0.2%. It's still very low, but it's much higher than what we used to get. So that's why we say that the synthesis is very difficult. Now, during the chemical synthesis, any enantiomer can be formed. Therefore, asymmetric synthesis is used. Asymmetric synthesis means that we are making only one particular enantiomer, that is the useful one. And this goes in line with the 12 principles of green chemistry, which means that we're going to limit wastage. And why is it so difficult? Because it has 11 chiral centers, which means that you can try to imagine how many different possibilities is there to have mirror images of that molecule. So 0.2% yield is actually kind of good, considering the different things that we need to monitor. Now we're going to consider the synthesis of part of that molecule of taxol. Let's see part of it. We call this a side chain that has to be synthesized, and this side chain has 2 chiral carbons. Yeah. And because it has 2 chiral carbons, this can lead to a series of different stereoisomers, and these stereoisomers can have side effects, and we don't want this. We want only one particular enantiomer. So then what we do, we use what we call chiral auxiliaries. What are chiral auxiliary? A chiral auxiliary is a molecule that is temporarily bound to the starting material. Let's say I'm going to take a very simple example, propanoic acid. So I'm going to replace one of the H here by NH2. So because this carbon now is attached to NH2, COOH, CH3, and H, so it becomes a chiral center, carbon attached to 4 different groups. Now, you can have 2 enantiomers, one where the NH2 is in front, one where the NH2 is at the back. Now, what we do, we insert a chiral auxiliary. So the chiral auxiliary is going to be inserted here temporarily. And this is going to provide steric hindrance. So this molecule might be big at the back, which forces the NH2 to be inserted in front of the plane, which means that we do not get 2 enantiomers, but we get only one. This one is not going to be produced because the chiral auxiliary is bulky at the back. And once we get the required enantiomer, we're going to remove the auxiliary. The chiral auxiliary is removed. Right? So both sides chains can be synthesized, but when you add the chiral auxiliary, it's going to temporarily bind to the starting material, and due to steric hindrance, the other incoming reactant binds to the desired site. This is what it means. So we are synthesizing in a stereospecific way, only what we need. And then once we're done, the auxiliary is removed. You can read more about how polarimeter, which we mentioned in 20.3, how polarimeter is used to verify what molecule we have synthesized. So if we are looking for a specific enantiomer, it's going to rotate plane polarized light in a specific direction by a specific angle. And if we have mixtures or if we have impurities, then the angle is going to change. So by verifying the angle by which light is rotated, then we can identify what enantiomer we have produced. We can verify the purity of what we have produced. And generally, when we are synthesizing pharmaceutical drug, we try to be stereospecific, because one of the isomer can be less active, can be inactive, or can even be harmful. And we try not to go in that direction to put patients at risk. And when we're making new drugs, we try to make only one of the isomer. The other stereoisomers are rigorously controlled and kept as low as possible. So with this, we finish D.7.